Welcome to The Explainer. Today we're going to tackle one of the most fundamental and, honestly, one of the weirdest ideas in all of physics. It's this invisible force that shapes literally everything, from the water you drink to the Wi-Fi that's connecting you to me right now. Okay, let's just dive right in. We're talking about the electric field.
I mean, really think about it for a second. How can one thing push another without ever touching it? Like when you rub a balloon on your hair and it just sticks to the wall? Or you get that little zap from a doorknob? There's no string, no wire, nothing you can see connecting them. So how is that possible? How can a force reach across what looks like just empty space? This isn't some new puzzle, by the way. This question totally stumped scientists for centuries.
And for a long, long time, they just gave it a name. They called it action at a distance. But, naming something doesn't really solve the mystery, does it? It just kind of puts a label on it. It felt like magic. It completely broke the #1 rule of common sense, which is that to move something, you got to touch it. This was a huge, huge roadblock to understanding how the universe really ticks.
So, how did we get past this whole invisible push problem? Well, it all started by asking a question that sounds almost ridiculously simple.
This quote right here, it just perfectly sums up the whole paradox. Okay, so imagine you've got a charge, let's call it big Q, and it's pushing another little charge, little q. Simple enough, right? But now, take that little charge Q away. What's left? What is in the space where it used to be? If the answer is nothing, then how does that nothing suddenly know to exert a force the instant you put Q back? It's such a brilliant question because it forces you to completely rethink what empty space actually is.
Yeah, to solve this, it took a massive conceptual leap. And it came from one of the true giants of physics, Michael Faraday. What's so amazing about Faraday is that he didn't have a lot of formal math training, but his physical intuition, it was just off the charts. And he proposed an idea that would literally change physics forever.
So what was Faraday's answer? It was to say that space isn't empty at all. He suggested that it's filled with something he called a field. And this was a total game changer.
Okay, so first things first, let's define our main character here. The charge that's doing all the work, our big Q. We call that the source charge. Think of its job as creating an influence, changing the very fabric of the space all around.
And this slide really shows you the huge shift in thinking. The old idea, over on the left, it's just mysterious, right? Almost magical. Charge Q just somehow reaches across empty space. But Faraday's idea on the right is so much more powerful. The source charge, Q, doesn't push the other charge directly. No. Instead, it creates a condition, an influence in the space all around it. It creates a field. And then when you place another charge, Q, into that space, it's the field itself, right at that spot, that does the pushing. The field is the go-between, no more magic.
And this gets us to the official definition. We can figure out what the electric field is doing at any point in space by asking a simple question. We imagine taking a tiny, positive test charge and placing it right there. What force would it feel? The direction and the strength of that potential force, well, that is the electric field at that point. This is so cool because it lets us map out the potential for a force everywhere, and that map exists whether there's a second charge there to feel it or not.
Okay, so this field is a real thing, but it's totally invisible. So how in the world do you draw a map of something you can't even see? Well, Faraday had a really intuitive answer for that too.
Yeah, Faraday, being the visual thinker he was, came up with a way to see the invisible. He originally called them lines of force, but today we know them as electric field lines. They're basically a picture, a map of this invisible field.
And the rules are really simple and elegant. Remember our imaginary positive test charge? Well, it would naturally get pushed away from another positive charge. So pretty simple. Electric field lines always point outwards, away from positive charges.
And, you guessed it, the opposite is also true. Our little positive test charge would get pulled toward a negative charge. So, the field lines always point inwards toward negative charges. You can already start to see how this gives us this beautiful, intuitive picture of all the forces involved.
So these few simple rules actually give us a ton of information. Lines start on positive, they end on negative. They can never, ever cross.
Why? Well, think about it. If they crossed, the force at that one spot would have to point in two directions at once, and that's just impossible. And maybe the most important rule, how close the lines are to each other shows you the field's strength. Where the lines are all bunched up, the field is super strong. Where they're spread far apart, it's weak. It's an incredibly clever way to draw an invisible force.
Now, I know this might all seem a little abstract, but this whole idea of the electric field is absolutely everywhere. So let's bring it back to the real world and look at why it matters so much.
So, one of the most common ways you'll find charges arranged in the universe is what's called an electric dipole. It's just a team-up of a positive and a negative charge, equal and opposite, separated by a tiny little distance. This simple little pair is a fundamental building block of, well, almost everything.
And you are definitely 100% familiar with the super famous dipole, the water molecule, H2O. The way the hydrogen and oxygen atoms are arranged means one side of the molecule is a little bit positive and the other side is a little bit negative. It has what we call a permanent electric dipole. And that right there is why water is such an amazing solvent. It's why it has all the properties that make life on Earth possible. All thanks to this little dipole.
But this all leaves us to the most important point of this entire explainer. The electric field isn't just some mathematical trick. It's not just a clever way to draw things to make calculations easier. For a long time, that's what a lot of people thought, but the truth is so much deeper. The electric field is a real physical thing. It's as real as the device you're watching this on.
So what makes it real? Well, it has a life of its own. It can change, it can ripple, it can evolve all on its own. And, most importantly, it can carry energy and it can transport information from one place to another. So if you wiggle a charge over here, the effect isn't felt over there instantly. A ripple, a disturbance, is created in the field, and that ripple actually has to travel across space.
And just how fast does that ripple travel? It travels at the ultimate cosmic speed limit. That's right, c, the speed of light. This is the profound connection. The field is what explains that time delay that physics requires. Cause and effect aren't instantaneous. The message has to travel.
And here it is, the final payoff. Those ripples in the field are electromagnetic waves. That's what light is. That's what radio waves are. Microwaves, the Wi-Fi signal bringing this to you right now, that is nothing more than energy and information being carried to you by a very real, very physical, oscillating electric field. So we end right here. We started with a pretty simple question about a push without a touch, and we ended up at the foundation of all modern communication. It really makes you wonder, doesn't it? If this invisible architecture of electric fields is the bedrock of so much of our reality, what other unseen forces, what other fields, might be shaping your world right now in ways we haven't even begun to imagine?